Yeah, namaste and welcome everyone to the Transitional Artificial Intelligence Research Group Seminar Series. This week we have Omkar Kulkarni from BITS Goa, and he's presenting this from Greece. This is intern there. The topic is Bayes-CATSI, and what is CATSI? It's a model for data imputation in time series, and the focus of this presentation is medical time series data using deep learning-based data imputation. And Omkar has been doing a research project with me online, and this is a product of that research project, and the paper is under review in a Q1 journal. Thank you, Omkar. You can begin.
Okay. Hello all. I'm Omkar here, and today I'll be presenting our latest work, which is Bayes-CATSI in the domain of medical time series data imputation. So I'll begin this presentation with the introduction, followed by the data, methodology and framework, followed by the results, discussion, conclusion, limitations, and future work. So, coming to data imputation, imputation is basically the process of replacing missing data with substituted values. So, in a time series context, the temporal structure and the cross-sectional correlation of multiple time series needs to be retained while imputing values. So accurate imputation of missing values in medical time series data is important for ensuring data quality and producing reliable data-driven predictive models. Uh, Now coming to the background, so previous work in this field includes models like Brits, CATSI, mice, and 3D mice. I'll elaborate on each of these. So Brits basically introduced a bidirectional RNN model which was successful in capturing the local cross-feature correlations along the tem along the tempo along with the temporal dependence of the missing values, that is dependence on past values. But the flaw of Brits was that it wasn't able to capture the global structure of a time series that we have. So CATSI did exactly this. So CATSI basically improved the local structure of the Brits model and introduced a context-aware imputation model, which was successful in capturing the global along with the local dependencies. Now coming to mice basically iteratively imputes missing data by modeling each variable with missing values as a function of other variables. That is cross-sectional imputation of missing values. So 3D mice basically combines mice with longitudinal Gaussian process models. However, the authors of CATSI showed that CATSI performs the best among all the models. So all the previous models that we introduced, that we spoke about, like Brits and CATSI, use deterministic deep learning models. Deterministic deep learning models basically use fixed weights, which have uncertainties associated, which need to be quantified. So that's why we basically introduce Bayes-CATSI and partial Bayes-CATSI, which develop on the CATSI model and provide uncertainty quantification of the imputation results along using variational inference. So the goal of this work is to provide a framework for uncertainty quantification of medical time series imputations and compare the results of our models with CATSI in case of individual missing values and consecutive missing value cases, and also provide an idea of the distributions of the outputs predicted by Bayes-CATSI. So the data that we used is from the physionet.org website, Computing in Cardiology Challenge 2018. We basically use 12 medical time series. Um, there are six brain channels recorded using electroencephalograms, one channel from electrooculograms, one from electromyograms, two respiration signals, one SaO2, that is saturation of oxygen, and ECG wave, which is from electrocardiogram. The frequency of all of these time series was 200 hertz. So these are the plots of the 12 time series that we use for one of the patients. As we see here, the 12 time series are a mixture of stationary and non-stationary. So we use both stationary and non-stationary time series in our analysis. Now coming to the methodology and framework, the first step is data pre-processing, and in this the first step was to generate the observation and evaluation masks. So basically, our raw input or our raw time series had certain missing values, which we refer to as ground truth missing values, and we add or we mask a few other values in all these time series, and we refer to these as masked missing values. The reason for masking is so that we can basically evaluate our deep learning models. So the observation mask basically keeps a track of the ground truth along with the masked missing values, while the evaluation mask keeps a track of the masked missing values. The next step was to get a pre-completed input, in which we basically use the temporal decay factor to fill up the missing values with temporary values. And the intuition behind the temporal decay factor is that if a value is unobserved for a long time, then it gravitates towards a default value, which is the empirical mean in our case. So this figure here gives an example of the mask generation process. We have three example time series here: F1, F2, F3. N represents the time steps. We arrange these time series in the form of in the form of a matrix with m samples or m rows and f columns. The red crosses here represent the ground truth missing values which are present in all these time series. We mask a few other values which are represented by green plus signs, and we then generate the observation mask and the evaluation mask. The imputation model then outputs the imputed values of all the time series, of all the missing values. And as we see here, we use the green dots here, which are basically the imputed values of the masked missing values, to evaluate our deep learning models. Coming to the variational inference part of our work, basically variational inference assumes a prior, and in our case we assume a Gaussian prior, where theta represents the neural network model parameters. So now the goal is basically to find the parameters of a variational posterior which is closest to the true posterior, where the variational posterior is denoted by Q and, and parameterized by delta, and the true posterior is denoted by P, where D represents the data. So now when we come to the mathematical aspect of this, we basically want to minimize the KL divergence between the variational posterior and the true posterior. So when we expand this, we get the following integral. When we further simplify this expression, we get this final expression, which is basically the KL divergence between the variational posterior and the Gaussian prior, and the likelihood cost, and the summation and the likelihood cost which is added to the scale divergence. This expression is known as variational free energy or expected lower bound. So basically, our loss function comes out to be the summation of a prior dependent part, which is referred to as the complexity cost, and the data dependent part, which is referred to as the likelihood cost. So there is a there is a trade-off between between satisfying the complexity of the data and the simplicity of the prior. Now the question is, how do we calculate the complexity cost, which is the KL divergence between the variational posterior and the prior? So the paper by Blundell et al., Bayes by Backprop, proposed a way to simplify the loss function using using Monte Carlo sampling as given below. So here we see that basically the simplified form of our loss function comes out to be the summation of the log of the variational posterior minus the log of the prior added to the likelihood cost, where theta I represents the ith sample drawn from the variational posterior. So the algorithm here gives us an idea of how the how the model works. So as we see here, the variational parameters that we have are is delta, which is comprised of the mean, and rho. Rho is used to calculate the standard deviation of the variational posterior in this way, in which we basically in which we basically calculate the log of 1 plus exponent rho. We basically use this log expression to keep the standard deviation positive, and epsilon is basically the white noise. So we calculate the variational loss here, and then we calculate the gradients of the mean and rho, and then update the variational parameters in the next step, where gamma is the is the learning rate. Another feature in this variational inference that Blundell et al. Had introduced is that they had used a scaled mixed prior. So what they did was they used a common prior to initialize the distributions of all the neural network model parameters. So they basically used a Gaussian prior, which was a scaled mixture of two Gaussian distributions. So since a common prior was used, we have we have chosen the hyperparameters of the scaled mix prior after careful optimization. Coming to the models that we propose are Bayes-CATSI and partial Bayes-CATSI. The common components of all of these two models are context-aware recurrent imputation, cross-feature imputation, and fusion layer. The details of these have been explained in the will be explained in the subsequent slides. The differences between the two models is that Bayes-CATSI uses both Bayesian LSTMs and Bayesian GRU layers along with the Bayesian MLP layers, while while partial Bayes-CATSI only uses Bayesian MLP layers. So that's why Bayes-CATSI is more computationally intensive, while partial Bayes-CATSI is not, which basically allows us to test partial Bayes-CATSI on a higher amount of data or the cross section of data. Hence, we test partial Bayes-CATSI on 2000 samples, which corresponds to 10 seconds, while Bayes-CATSI has been tested on 500 time samples, that is 2.5 seconds. So here, this is a summary of the overall framework of both the models, in which the raw input along with the temporal decay factor is used to generate the pre-completed input, which is then input into the context-aware recurrent imputation model and the cross-feature imputation model. The outputs from both are fused using the fusion layer, which outputs the final imputation. So in this slide, I'll go into the into the details of the Bayes-CATSI. Uh, so coming to the context-aware recurrent imputation, we basically capture the context in two parts. The first part basically summarizes the basic statistics of every time series using a Bayesian MLP model, MLP layer, Bayesian multi-layer perceptrons. And the second part uses a Bayesian GRU layer to summarize the complex temporal dynamics. So the output from both of these parts are concatenated to get the context vector. This context vector, along with the pre-completed input and the evaluation and observation mask, is input into the bidirectional RNN layer, which then which then gives the output for the context-aware recurrent imputation component. Simultaneously, we have the output from the cross-feature imputation component, which uses Bayesian multi-layer perceptrons. So the output from both of these models is merged using the fusion layer to give the final imputation. Coming to partial Bayes-CATSI, as we see here, we have only used Bayesian linear layers here, and these layers are sparsely distributed in all of the components of the model. So this basically reduces the computational intensive nature which we found for Bayes-CATSI, and allows us to test our model on a higher cross section of time series. The final loss function that we then have is basically the summation of the losses from the recurrent imputations x, cross feature imputation z, and the final imputation. So this helps us evaluate evaluate every component of our model. So coming to the results part, we basically use the metrics normalized root mean squared error, in which the first component 1 minus m represents the observation matrix, as in the values which are present, um, where m is the missing rate. So 1 minus m is basically the observation mask, while x is the masked values, y are the final imputation output by our model. This this difference between the masked values and the final imputation is min max normalized, and then the root mean squared error is found. So coming to the results of partial Bayes-CATSI, as we see here, we have the analyte-wise results, and partial Bayes-CATSI is only able to outperform CATSI for three analytes, while for others it underperforms, and the overall performance of partial Bayes-CATSI is 3.76% worse than CATSI. So this is for the individual missing value cases. I- Now coming to the individual missing value results of Bayes-CATSI, we see here that Bayes-CATSI is able to outperform CATSI for 8 features out of 12, and overall it outperforms CATSI by 9.57%, which shows that it's better than CATSI in the individual missing value case. We also see here that the standard deviations for Bayes-CATSI and partial Bayes-CATSI are low. So this shows that the uncertainty in the predictions of partial Bayes-CATSI and Bayes-CATSI is very less compared to CATSI. So these are the results for partial Bayes-CATSI in the consecutive missing value cases with missing value lengths from m is equal to 2 to 5, in which basically the missing values are consecutive with the lengths as given. So here we see that partial Bayes-CATSI performs better than CATSI for m is equal to 3, 4 and 5 with a peak performance of 4 of length 4. While in Bayes-CATSI, the Bayes-CATSI model has a minimal advantage over CATSI for missing value lengths of 3 and 5 at 0.24% and 0.05%, while while it underperforms CATSI for missing value lengths of 2 and 4 at 7.37% and 9.75%. So we can observe that partial Bayes-CATSI performs better compared to Bayes-CATSI for for the consecutive missing value cases. So here we give the viewers an idea of how the missing values are generated. So this is one of the time series that we consider, and these are the first 500 samples, and as we see here, the imputed values have very low standard deviations. Hence, the 5% confidence intervals, 95% confidence intervals, and the imputed values are pretty close to each other, which shows that the uncertainty in in the predictions of Bayes-CATSI is low. So here we basically give the viewers give the viewers an idea of the uh, output of the outputs of the imputed values given by the Bayes-CATSI model, where sample number represents the sample number in the previous graph, in the previous plot here. So as we see here, the distribution of the output varies throughout all the samples. The red line on the left side represents the 5% confidence interval, while the right line represents the 95% confidence interval. So coming to the discussion of the results, the standard deviations are lower for partial Bayes-CATSI and Bayes-CATSI compared to CATSI. Thus, there is lesser uncertainty in the predictions. Partial Bayes-CATSI underperforms CATSI by 3.76%, while Bayes-CATSI outperforms CATSI by 9.57% for individual missing value cases. While for the consecutive missing value cases, partial Bayes-CATSI performs better. Hence, basically, the results demonstrate that the usage of Bayesian LSTM and Bayesian GRU layers captures the complex temporal dynamics using variational inference and provides a better performance in the individual missing value case. So coming to the conclusion, in this paper, we basically developed two frameworks for uncertainty quantification for the medical time series data imputation problem. So it can be clearly seen that Bayes-CATSI shows superior performance and represents a significant advancement in the field of clinical time series imputation using uncertainty quantification provided by variational deep learning layers. So now we come to the limitations of our work. So basically, due to computational constraints, current models have been tested on lower sample sizes. Also, the variational inference requires requires a prior, and in this work, the prior is assumed to be Gaussian. And convergence issues might arise due to multimodal and irregular posterior distributions, which can be addressed in future work. So the future work can focus on basically expanding the dataset size and integrating MCMC sampling into Bayes-CATSI as it samples directly from the posterior, while variational inference is an approximate approach. Now I'll move on to the code repository in which I'll try to explain the code. Is my screen visible?
No, yeah, it's visible. Yeah.
Okay. So this is the code repo for our work, and I'll explain the code for Bayes-CATSI. Basically, the file which the users have to run is main.py, which contains the deep learning model that runs the the epochs. The file model.py contains the code for Bayes-CATSI. And utils contains all the utility functions that have been used in the work. The module Bayesian basically has the list of all has the codes for all the Bayesian deep learning models. So coming to the loss function in this Bayesian model, we have the calculation. We have the code for the divergence, which is basically the log of variational posterior minus the log of the prior. Also, this file contains the code for the sampling and elbow function. Here, the criterion output comma labels basically represents the likelihood cost from the loss function that has been explained in the slides, and this is the complexity cost, and we use a hyperparameter complexity cost weight, which is multiplied to the complexity cost here. The file weight.py basically contains the code for the variational posterior and the scaled mixed prior, which is basically the combination of two Gaussian distributions with standard deviations sigma 1 and sigma 2. And the code for partial Bayes-CATSI has been arranged in a similar way.
Okay, thank you.
Thank you. Yeah.
Omkar, this was excellent. So, could you go back into that folder of utils and just show what you meant by the utility function?
Sorry, sir, could you repeat?
The utils folder, the utility folder, what
Yeah,
utility
okay.
code was there?
Yeah, okay. This one,
Yeah.
utils.py. Okay. Yeah. So utils.py basically contains the data loaders, which is used to load the raw data, and also calculate the observation mask and the evaluation masks.
Okay, that's good. Thank you. Right, thanks. On the floor for questions and answers. So, anybody? Yeah, sure.
I always have questions.
Just a second. Give me a second. Right, we have John Hawkins from Playground XYZ.
Yeah.
He's a chief scientist there, and he has some questions. Thanks, John.
Awesome. Thank you, Omkar. Really enjoyed that presentation. Couple of questions.
Yeah.
When you were doing the inference over multiple steps, what was the methodology there? Did you do sort of impute initial steps and then feed them recursively in, or was the model doing the imputation of each step completely independently, with sort of null values being just always aware that there were null values around it?
Actually, I don't understand. Could you explain the two cases again?
Yeah. So if you're imputing a single value, you've got real values either side of it if you're using the sort of bidirectional network. So it's just got real values coming before it, real values after it being fed in for that imputation. When you've got when you're masking out multiple values as missing, then you've got two options. You've got multiple options. One is you impute the first one and then feed that in as a feature to impute the next one, and then feed those two as a feature to impute the next one. Or your model deals with nulls and you impute all of them independently.
Okay, okay. I understand. Yeah. So I'll just present the slides. The answer is in the algorithm in the slides. Just a second. So basically, what I'm doing is I'm basically masking the missing values first, and then after that I basically use the temporal decay factor to fill in all the missing values,
Okay.
and followed by this, now the new pre-completed input is used to generate the new imputed values.
Understood.
So the pre-completed input is probably the answer to the
Yeah. Okay.
query.
Understood.
Yeah, yeah.
Yeah. So, okay, excellent. And I think a couple of slides after this, when you were showing the results, you showed there's actually a time series plot where you're actually showing the imputations with, I think, the red crosses
Yeah.
at the top of the plot, the time series plot. Yeah, that one there. So, because one of the questions I wanted to ask is, in the real world, missing values are not necessarily IID. They can be either, especially across multiple time series, they might be related to each other, or they can be caused by something that's affecting other signals, other noise. And when I
Yeah.
saw this, it looks like all of the missing points here that you've imputed are all at the top of the series. So do you have why is it that the imputations seem to be happening at the peak of the series?
Yeah, so the thing is that basically coming to the first point, in the real world, as you said, there might be cross-feature correlations between multiple time series. So the component in our imputation model, which is the cross-feature imputation component, basically captures all of these correlations. And coming to the next point, in this particular time series, all of the imputed values are on the top of the figure, on the top of the plot. This is just an example plot actually, which has been used to show the time series. So in this particular example, they are on the top of the plot. All the values are higher compared to the normal. Yeah.
Okay. Okay. And final question. It'd be interesting to know, because you're looking at multiple time series with cross features, but they're not all of those features necessarily. They come from different devices. So you've got the EEG signals, which would be somewhat similar to each other from the brain, but then you've also got the ECG and then other biometric signals. Did you look at what was the value of those different time series in imputing others? Like, would it be, for example, you might expect that the EEGs are a greater source of signal for imputing other EEGs as opposed to the other biometric time series? Does that make
Oh, so you
sense?
mean how much weight is given to other
Yeah.
features in imputing the model? Okay, so that actually has been done internally by the cross-feature imputation model. I didn't specifically go into the cross-feature imputation model and check the weights that were given. So that may be the future work that we can do.
Okay, cool.
Yeah.
Thank you.
Thanks a lot, sir. Yeah.
Thanks, John. Anybody online who has a question? Anybody online? So, anybody
No.
here? All right, yeah, Rodney, you have anything?
No, I'm fine with this. It's really good work, I think. So yeah, so that'll be my only comment. Thank you.
Okay, just anybody here has a question or Mochi?
Oh, nice. That was a nice one.
Okay, people are very happy with your work. So I have few questions, just minor
Okay.
ones. So the CATSI model, that's what is so special in the CATSI that it deals with the medical domain, and can the CATSI and Bayes-CATSI be used for other types of problems such as time series data imputation for rainfall or drought and kind of problems? Yeah.
Right. Yeah. So basically, we have used the I have used the CATSI model because all of the models that I mentioned, Brits, mice, 3D mice, and all of these, the authors of CATSI have shown that CATSI outperforms all of these models. So that's why I used CATSI and then developed Bayes-CATSI. So the idea behind Bayes-CATSI is that basically it tries to capture the temporal dependence, the local temporal dependence, along with the local cross-feature correlations that Brits does. At the same time, it captures the global temporal dependence and the global cross-feature correlations for any time series. The application that we have used is medical time series, but we can expand this to climate as well, like climate time series and any kind of time series.
That's excellent. So you have developed a model that can be used for climate or economic, financial, Bitcoin, and anything else out there, which has a time
Right.
series. And then we are giving the code
Okay.
along with it.
Right.
Now I have a question. Now I do have a question.
economics.
Just
It was Bitcoin that got in.
Yeah,
My
go ahead.
question is, okay, this works for time series.
Right.
So I've got sort of two questions. Could this be extended to, or could this work for spatial interpolation, spatial data imputation, right? Because spatial processes, some similarities to time series, but there are also some differences. Right, because spatial autocorrelation goes in multiple directions. It doesn't just go in sort of the one direction. And secondly, extending beyond that, what about could it be applied to spatiotemporal type models where you've got both a spatial and a time series component to it? Because when one's talking about climate data, for example, a lot of climate data that falls into that sort of category where there's both a spatial and a temporal component to it.
Right.
There are statistical methods such as INLA, for example, for dealing with spatiotemporal dynamics. So I'm wondering whether, and there's often missing spatial data, you see, right, as well as missing temporal. So that becomes the question whether this couldn't be adapted to that more general setting.
Right. So we'll have to investigate the spatial aspect. So when we talk about spatio-temporal time series, maybe we might have to investigate graph neural networks, which can be used with Bayes-CATSI. But Bayes-CATSI is only for only for temporal time series.
Yes.
So we have to investigate the spatio-temporal aspect as well.
Right. So
That
this is
can be
another
a
possible
future.
extension. So
Right.
Yeah.
Right. Right.
Something he said for each implant the MCMC feature of the spatial temporal might come.
The MCMC sampling in the future work, it's more for the posterior of the weights and the biases, not for imputing data, but you could use MCMC sampling for imputing data as well. Yes, Ratni has a question.
I'm sorry, I may have missed this in the presentation, but when you are imputing data, to what extent can you impute data? What I mean by this is how much data needs to be present in order for you to get good imputations? What's the minimum amount of data availability that is required for this imputation method to actually be useful?
Okay, okay.
Right.
So basically, we had computational constraints. So that's why we have investigated this on maximum 2000 samples, which is like 10 seconds. But this has not been investigated as to what the minimum amount of data has to be there to give accurate results. So maybe for that we might need higher amount of computational uh, resources.
You could
Yeah.
simulate that by having different amounts of masking in the samples. Like some samples have more masking, some samples have less, and then look at performance over that, and that would help.
Right. Yeah, right.
Yeah,
Different sizes.
Okay,
Different
so
numbers of this.
Yes.
yeah, I think that's
Okay.
a great suggestion by John. I think that would be useful to know.
sorry,
Be-
Ratni, could you speak up a bit, please?
Oh yeah, sorry. I think it's a great suggestion by John, where we can increase the amount of masking that is happening in the data. And also the reason why I'm asking this question is because of the nature of data that we get in the real world. You will have a lot of missing values across regions, right? For example, rainfall data, you will have some rainfall and then you won't have rainfall for months in the desert areas. Then you'll have some rainfall again. So will Bayes-CATSI be able to extrapolate or interpolate whatever it's doing in those missing months to get that larger trend?
Just to note there, is like missing data is not the same as no data, basically in your example. So like if there's no rainfall, was that's not missing data. That is just there was no rainfall, but that was recorded that there was no rainfall, right? So I guess you were not referring to that. Probably your example is more going towards where you have large chunks of missing data. So I mean, I'll go back to Omkar with this because in the case of rainfall, you have data missing, but then you may have other, features associated with the rainfall, such as humidity or
Yeah.
temperature and other things which may be present, right? So how
Yeah.
does your
Right.
CATSI work with multi-dimensional or multivariate features? And
Right.
in your experiments for the medical time series, you did look at multivariate features, right?
Right. The cross feature imputation component of the model does exactly that. It looks at multiple time series.
Right, so that's good. So, okay, I'll just summarize some future work here. Probably that was not very obvious, but it's becoming more obvious with all this discussion. So first is like, one is future work is applying Bayes-CATSI to other problems, economics, finance, and climate problems, right? The other is looking at spatio-temporal data reconstruction or data imputation with Bayes-CATSI. So some of you are doing PhD here looking for topics, right? So that's spatio-temporal with CATSI. That's going to be a good topic. Third is to see if it can be used for just spatial data reconstruction, right? And we are doing something like that in our group at the moment. Shuan, our postdoc, she's not here today. She's looking at reconstruction of data, that remote sensing data, that where the cloud comes in there, and then how do you reconstruct that? So she's finding more of a deep learning approach for that. So there are other problems where there's data missing or problems, and that happens in radiology and medical data as well. So how do you extend these things in that domain? So that's all great. Just want to say thank you to Omkar, and one more thing is that this was a very unique project. Omkar, we physically met, but just the weekly meetings and stuff. And Omkar is a final year student, right?
Yeah, I am in my 5th year.
And we did this project in 6 months' time, right? And basically, Omkar didn't know Bayesian inference, very little, I guess.
Yeah, yeah.
So he went through my lecture videos on Bayesian inference, and he studied with Kapoor's variational Bayesian inference code. And I don't know, I think I don't know who came with this idea. It was me and Omkar. It was probably a joint thing, what to do with this project. We were just brainstorming, and Omkar came up with some time series medical data. And he said, okay, this is this. I said, let's do data imputation. Then he did the literature. He brought the CATSI model, and I said, why don't we do a variational based version of it? And he's like, all right, but. And I said, okay. So this is how we went to and fro, and then he wrote the paper, and very fast we submitted the paper to journal experts with applications, and it's in archive. This was all done in 6 months' time. Just a final thing that I would like to ask Omkar, because this video will be seen by other people in the group, is what's your next move? What you are doing next with us? Could you tell about that project?
Yeah, so the next work actually that I plan to do is in the field of precision medicine, um, wherein we basically use graph deep learning, and we basically add a Bayesian component to this uh, learning, and try to simulate the diastolic left ventricle diastolic movement, or the displacement of the left ventricle in the heart, simulated using Bayesian graph deep learning. So this is one of the problems that I'm looking at right now on the graph deep learning side of the field.
And with this, we are trying to establish a collaboration with the University College London researcher who is a lead cardiologist in this area. So thanks, Omkar. Okay, everyone,
Thanks a
I
lot.
will just end the recording. Thank you very much, Omkar.
Thanks a lot for the